So let's create a example, a simple example on how to simulate a cantilever beam. So what are all the options that we have? Okay, so let's take a simple cantilever beam design. So here we'll go to layers and we'll have two layers. So just rename this as bottom and layer 2 as top. Okay, so here it's in the alphabetical order. So if we want to see the layer order, it is this way. 0 is the bottom layer and top layer. Okay, so this is the layer order. Okay, so don't get confused with the layer order seen here. Okay, so let's draw something in the blue in the bottom layer. So let's create a small rectangle. So this is a standard example which I'm taking, which most of the books um, take this model for explaining the mechanism of cantilever beam. 0, 0, 300, 100. So I'll go to top layer. So I repeat the same coordinates. Take a rectangle 0, 0 and 300, 100. So two layers. So let me save this. So I save this file and open 3D Builder, import this file. So I have two layers, layer 0, modify height. So I'll maintain it as 10. So we are changing its thickness. So I'll even maintain this 10 as well. So here we have created two rectangles, but we don't see a gap. So for that, we can go to this option where we can add a level. So it asks, it will have an option to enter above layer 0. Yes, we want to enter, we want to introduce a layer above 0. So we click OK. So that is a blank layer. So selecting a blank layer. So now this layer 2 is got shifted. So we have a blank layer. So we modify its height and we maintain this somewhere 5 micrometers. Okay. So this is what we do. So now we see a gap between the two. Okay. Yeah. So let's save this file. Let's export this module design to analysis module. So now we have this model here. So first let's do a simple uh, electrostatically actuated beam. So I click apply. Okay, I've selected thermal electromechanical relaxation. Click apply. Okay, material. So I select each material. If we don't apply material property, everything is considered as polysilicon. In this case, I'm applying silicon 100. So you can decide on the material of your choice. So select entity. On the top entity, I enter value, say 25 volts. At the bottom, enter 0 volts. So I go to boundary, fixed. So I'm fixing the boundary, the bottom. Click OK. So all the three sides are fixed. Sorry, not this one. This one. So all the three faces, bottom and side, are fixed. So three faces. So here we can set the mechanical mesh only on, we can set the mesh only for the model that we are interested. So anyways, the bottom layer is fixed, so it's not contributing anything for the deformation of the structure or the working model of it. So let's not mesh it. So for the other, I just mesh a very coarse one, 50. Okay, so let's do this analysis. So here we see the displacement happening. So it was set, a random value of voltage is set. So here, so this is the displacement that we have. Okay, so this is how we can do a simple electrostatic actuation simulation by applying voltage to both of these entities. So here there are few things which may be interested to many of us, is what happens if one of the boundary condition is removed on one of the sides. So I delete all the boundary conditions. Let's see this. How does this work? So I repeat the boundary conditions again. So this time I'll be applying only for one side of the cantilever beam. So let the voltage be as it is. So I'll clean up the previous analysis and then start static analysis. So on one side it is free and one side it is fixed. Okay, so here we get the displacement more on one side, because here one end is fixed and another end is free. So in the earlier case both ends were fixed, so naturally the displacement was maximum in the center. Okay, so here this is what we can extract this data. Okay, so here if you wish to get the simulation animation, so you can choose this. I just emphasize to just to have a better view, so you can see that there is a small displacement that is happening. Okay, so here we can extract this displacement data and we can get the capacitance data. Okay, so this is the capacitance between the two, 58.68 femtofarads. Okay, so here we can also get the stress invariance. So to have a better view, so you can remove the mesh and play the animation. So here we can see the displacement that is happening. So this was on the displacement due to the electrostatic force. So I stop the simulation. So if we wish to do electrostatic simulation and get the pull-in voltage plot, so we can do these options. Naturally, it will take a very long time to do these simulation or contact analysis. Let's apply voltage in the top, some 0 to 50. I keep it very coarse in the increment of 10. So you can refine the increment. So keep a even increment between the two values. And another voltage that we apply is at the bottom, that is 0. Okay, so let's clean up the previous analysis, and then we go to phase pair definition, select it. So now go to phase A. We define the bottom face of the top layer to be the phase A. Click OK. Again, go to contact, phase pair definition, contact rigid B, phase B. So if you are unable to select in the gap provided, so you can always consider this option of increasing the distance between the two. So it's not physical distance, it is just a expanded view of the gaps. Okay. And then we again go to phase pair definition, complete pair. So double click on this, it gets enabled. So we have only one pair. Okay, so we have only one pair here. We accept. Okay, so ensure if it is activated. Yes, it is activated. Okay, so I come back to the original view. So now let's run the simulation. So this will take for a while. So the simulation is complete now. So now we go to results and we can check the displacement. So for the applied voltage, so here it is showing the final result meaning we have applied voltage in the range of 0 to 50 volts in the increment of 10. So here the displacement which is showing is 0.05, which is at the last stage, that is a 50 volt stage. Okay, so if you want to see the results at every increment of the voltage, so you can see the voltage is set, the x-axis is set to voltage, and then the y-axis can see the displacement. So we get this curve. So here we can adjust the coordinate axis by double click on that axis. So you can play with these options. Okay, so you can set the x point and the y point axis. So when you click on the axis, you get this option to set the value of the range. So here, if you wish to increase the axis, you can just increase the axis as it is. Okay. So similarly for y as well, similarly for x as well. So here, if we want to extract the data, here we can double click on the plot and then we can click on data. So this gives us 5 different values. So to see a better view, so this is what at 10 volts the displacement is 2 nanometer, and 8 nanometer for 20 volts, and for 30 volts it is 18 nanometer, so and 32 nanometer and 51 nanometer. Okay, so this is the displacement that we get. So we can just copy this option and paste it on the Excel sheet to plot these, or to do any data plots. Okay, so this is how we can plot the displacement value. So say for instance, we wanted to get the plot at somewhere in the center. So we want to see what is the displacement happening in the center. So for that, we select this option, node curve, magnitude, and then the result that is shown is displacement. So when we click at a certain point, it plots the value of voltage versus displacement at that point. Okay. Similarly, we can plot the x and y displacement and also the capacitance if we wish to. So this the capacitance data. So we select and click OK. This plots the capacitance versus voltage. Okay. Okay, change in capacitance versus voltage. And now let's try to apply a pressure load on the same. So let's try to apply a very small pressure, 1 E minus 3. So that's 1 kilopascal. And here, clean up the previous analysis. And then we can start static analysis. Okay, so here we have selected thermoelectromechanical relaxation that has to be reset back to stress displacement. So we are applying pressure load. So naturally there is no electromechanical simulation. It's only purely a mechanical simulation. So that's why it gives us an error here. Please define at least 2 conductors. Now we have selected stress displacement. So everything should be okay to run the simulation. So simulation is done. Go to results, set displacement. So here you can see that the displacement is due to the pressure of 1 kilopascal. So we can enable disable mesh. So based on our requirement, we can do this. Stress invariance can be seen here, and then directional stress can also be extracted. Okay, so this was on the cantilever beam example. So it can be uh, used for multiple applications. So here there's an example how we can do an electrostatic based actuation and a pressure based actuation. Okay.